In this video, we work an example problem involving the lateral surface area of a solid of revolution. So we are given this information. We're told that the region is bounded by these four curves. So let's sketch it. My region is bounded by this curve. I think I'm going to do that last. The line y equals 2. The vertical line x equals 3/4. So if that's 1, 3/4 might be right there. And then x equals 15/4. That is a little bit less than 4. So it looks like it's 3 3/4. And this curve is y equals square root of x. It's just been shifted up 2 units. So when x equals 1, y equals 1 plus 2, which is 3. And when x equals 4, y equals square root of 4, which is 2. 2 plus 2 is 4. And then of course when x equals 0, y equals 2. So it's just that familiar square root graph. It's just been shifted up 2 units. That's what that plus 2 does. It's a vertical shift. Okay, so we're taking this region and we're revolving it around the line y equals 2. So you have something that looks like this. Now when I revolve this around the line y equals 2, I'm going to see that y equals the square root of 2, or x plus 2 graph reflected down here. The reflection is going to look like this. And so this is our reflected region. And that forms a solid of revolution. So that's what one end looks like. It's a little disc. Here's another end. Now if I want to find the lateral surface area, so that is the surface area of the solid of revolution, not including that end cap and not including this end cap, I'm going to slice perpendicular to the line y equals 2. When I do that, I end up with something that looks like that. On the other side, I can't see it. It's going to look like that. It's like I've got a strip of paper wrapped around my surface. Like I talked about in the last video. It's like that heat protector sleeve around the outside of your coffee cup. So if this is my surface, this is like the strip of paper that's been wrapped around it, like this. And actually it's going to be hugging the surface like it normally does when it's on correctly. Okay, so if I want the lateral surface area of the solid of revolution, I just need to find the lateral surface area of one strip, or one strip of paper that looks like this. Well, in order to find that surface area, I take my little strip of paper, and then I cut it on one side, kind of like I cut this strip. It's already cut. And then I unfold it. Now this doesn't look like a rectangle, but it's going to look almost like a rectangle in the limit. So it's going to look roughly like this. Then the surface area of that strip of paper is the same as the area of this little rectangle. And like I said, we can see from this, it's not exactly rectangular. It has a little bit of curvature to it. And that length, yeah, it's not exactly vertical. Okay, So then the question becomes, well, what are these dimensions? Well, this dimension all the way around, well, that was the circumference of that little disc. If I was using the disc method, I'm slicing the same way that I would slice for the disc method. It's going to be the circumference of that disc. So it's 2 pi times the radius. And careful here, this dimension is arc length. It's not delta x. Even though it looks like delta x in our picture, it's a little bit longer than that. So this dimension's arc length. And I know it looks like I'm talking about the bottom, but I'm not. It's that side. So the surface area is 2 pi times the radius times the arc length. Now, we can do this 2 ways. We can find this surface area in terms of x or y, even though our slices are vertical, like this. Even though that disc, if I was using the disc method, would have a thickness delta x. I can do everything in terms of x, or I can do everything in terms of y, and either way, I'm going to get the right answer. So let's do this problem both ways. First, let's do this in terms of x. We're going to come up with both integrals. So this is the lateral surface area. We're going to come up with both integrals, and one will be in terms of x and the other will be in terms of y, and then we'll just evaluate whichever one's simpler. It's not 100% obvious ever which one is going to be simpler. So let's look at our picture. In terms of x, my arc length is the square root of 1 plus y prime squared times delta x. Now the arc, or the curve, is given by this formula. So I've got y equals the square root. So y is a function of x, and it's equal to the square root of x plus 2. To take the derivative of that, I'm going to rewrite that. That's an x to the 1/2. It's this power over this power. Now we'll take its derivative just using the power rule. Derivative of x to some power is 1/2, or it's that power, times x to the 1 less power. And 1/2 minus 1 is negative 1/2. Derivative of 2 is 0. So that's our y prime. So we can substitute that in. And I'll simplify a little bit. That negative 1/2 power means I've got an x to the 1/2, but in the denominator. So this is 1 over 2, and I've got a square root of x, or an x to the 1/2 in the denominator. I'm talking about the ith x value. This should be the derivative evaluated at x sub I. And then if I want to square this fraction, I square the numerator and square the denominator. 1 squared is 1. Square all the factors. 2 squared is 4. Square root of x squared is x. We don't need that. An extra bar. That's where our radical stops. Delta x is over here. And we might get a common denominator. This has a denominator of 1. That has a denominator of 4x. So instead of writing 1, I'll just write 4x over 4x. And I'm just using the x sub I because I'm talking about the ith little strip of paper that we're wrapping around our surface. So I've got a common denominator now. In the numerator, I have the square root of 4x sub I plus 1. In the denominator, I have the square root of 4 times x sub I. Still simplifying. Square root of 4 I can do, so I will. That simplifies to a 2. Square root of x sub I, that doesn't simplify, so I'm just going to leave it alone. that is a beast. We could do it. We could evaluate the integral for arc length for this curve. And I think we'd have to use integration by parts though. Okay, so that's our arc length. Now I also want the circumference. As a function of x. So that's 2 pi r. If I want circumference as a function of x, that means I need r as a function of x. Now, because of our picture, we see that r is a vertical distance. It's the distance from there to there. So it's the top y value minus the bottom y value. But because of this delta x that we chose, this is the top y minus the bottom y in terms of x. Well, the top y value in terms of x is just given by the square root of x plus 2. So I've got, oops, not 2, square root of x sub I plus 2. That's my top y value. And the bottom y value that's on our axis, that's y equals 2. That's convenient. We're subtracting 2, so we just end up with x sub I, or the square root of x sub I as our radius. Okay, so now we can put the pieces together. S sub I is the circumference, so 2 pi times the radius, times the arc length. And so we get 2 pi, and the radius is right here. That's our r sub I. So I've got the square root of x sub I there. And our arc length, that's this guy up here. So we've got square root of 4 x sub I plus 1, all divided by 2 times the square root of x sub I. Oh, that's nice, guys. See it? Don't forget your delta x. That's part of the arc length as well. Look what happens. Those square roots reduce. Very nice. The 2's reduce as well. So we just end up with pi times the square root of 4x plus 1. That's the ith x value, times delta x. And that is easy to integrate. So if I want the surface area of this thing in terms of x, I'm just going to bring my picture back so we can still see what's going on. The surface area, the lateral surface area, that's around the outside, not on the end caps, is the surface area of the first piece plus the surface area of the second piece plus the surface area of the third, and we keep going until we get to the nth piece. And we say, adding all those terms like that is a little bit annoying. Let's come up with some shorthand. Somebody already did. We said, sum this as I goes from 1 to n for s sub I. So I plug in I equals 1, I get s sub 1. Then I add. Plug in I equals 2, I get s sub 2. And we keep going until we get to n. Now we just saw that s sub I is this. We did all that work. So s sub I is pi times the square root of 4x sub I plus 1 times delta x. And now if I want the surface area, the lateral surface area, I take the limit as the number of pieces goes to infinity, or alternatively as delta x goes to 0. I think I'm going to write it this way, 4x sub I plus 1, square root of something, is that something to the 1/2 power? And that's this, guys. It's the integral of pi times 4x plus 1 to the 1/2 dx. Now this is a function, this is not a surface area. If I want a surface area, I need bounds. To find our bounds, we go back to our picture and look at where x starts and where x stops. Now it looks like 1 and 4, but that's not exactly right. X started at 3/4 and x ended at 15/4. All right. Now if I want to find the surface area, I just evaluate this integral using whichever methods, whichever integration methods are appropriate. Now this time, notice I've got a function under a radical here, or a function raised to the 1/2 power. U substitution makes the most sense. So I identify my inside function, that's 4x plus 1, and I take its derivative with respect to x. The derivative of 4x plus 1 with respect to x is 4, so du is that derivative times dx. And I look up here and I see, do I have a 4x or 4 dx? I'm not even concerned about the 4. Do I have a dx? Yes. Excuse me. The constants can always be modified. So if I want a 1 dx here, I can take this equation and solve for dx by dividing both sides by 4. And of course, taking du and dividing by 4 is the same as multiplying by 1/4. So dx turns out to be 1/4 of du. So this is pi times u to the 1/2, and this is 1/4 of du. Okay. Now I'm almost ready to write my integral entirely in terms of u. I'm not quite there yet. My integrand is pi times u to the 1/2. And that 1/4 du, I can bring that 1/4 out front. That's 1/4 over there and a du to the far right. But I need new bounds. These bounds are x values. This says start with x equals 15 over 4 and end at x equals 3 over 4. That's what you're supposed to do. Well, we need to figure out what u is when x has these values. So we're going to find new bounds. To find our new upper bound, we're going to take this formula. So I have u as a function of x. It's 4 times my x plus 1. Put parentheses, that's placeholder notation. I'm going to replace the x with 15 over 4. And the 4's reduce. 15 plus 1 is 16, that's convenient. So our new upper bound is 16. When x equals this value, u equals 16. So that's my new bound for u. And these have to be u values because of that du right there. My new lower bound comes from doing basically the same thing. I just take my old lower bound and I substitute it into my formula for u. So I'm substituting in a 3/4 for x, substitute in 3/4 like this. The 4's reduced, just get a 3 plus a 1, which is a 4. So when x equals this value, u equals that value. That is my new lower bound. Now since we've changed the limits of integration, we never have to go back to x. This is it's not an entirely new problem, but this has already been written in an entirely new form. So I can evaluate this, and this is going to be equivalent to that. Okay, so let's evaluate this. Pi and 1/4, that can be factored out. And the antiderivative of u to the 1/2 is u raised to the 1/2 plus 1. We add 1 to the exponent. 1/2 plus 1 is 1/2 plus 2 halves. 1/2 plus 2 halves is 3 halves. And then we're dividing by the new exponent. Dividing by 3 halves is the same as multiplying by 2/3. You take it and you flip it. A 2 goes into itself once and into 4 twice. So now I've got a pi over 6 out front. Now we're going to evaluate this from u equals 4 to u equals 16. So I have pi over 6 times 16 to the 3 halves minus 4 to the 3 halves. That's our answer. It's just not simplified. Now, if you want to, you can simplify this, and this simplifies very nicely, so I highly recommend that you simplify this. Remember, x to the m over n is the nth root of x to the m, or you could do this one, the nth root of x to the m. So you do the power first and then take the root, or you could do the root first and then raise that answer to a power. When I'm working with numbers, I tend to do this one because taking the nth root makes it smaller. And then I take that small number and I raise it to a power. That's easier than taking a number and raising it to a power, which is making it really large, and then taking the nth root of it. I don't know those nth roots for very large numbers, so I'm going to do this instead. So when I see a 16 to the 3/2, what I'm thinking is, that's the square root of 16 cubed, and that is the square root of 4 cubed. Square root of 16 is 4, 4 cubed is 64. Square root of 4 is 2, 2 cubed is 8. 64 minus 8, what's that? Is that 56? So 56 pi over 6. And 56 is the same as, what, 27 times 2, and 6 is the same as, wait, is that right? No, it's not 27 times 2, it's 28 times 2. Excuse me. 28 times 2, and 6 is the same as 2 times 3. So those 2's reduce, and we get 28 pi over 3. Say, what is that? That is the surface area of our solid of revolution. So the lateral surface area of the solid of revolution is 28 pi over 3, and that's going to be units squared because it's area. All right, so now we're done with that one. Now let's take a look at exactly the same problem, but instead of writing the radius and arc length in terms of x, let's write it in terms of y and see if we like that integral better. It might be easier in terms of y. This one wasn't too bad though. It just required a little bit, the integration just required a u substitution, so that's not difficult. We're going to do exactly the same problem. We should still get 28 pi over 3, provided I did everything right the first time. And we're going to see how the formulas change when I think of the radius and arc length as functions of y instead of functions of x. Always try to use the same paper. Feel bad about all the trees. Okay. So this is the same problem, new method, or variation of the same method. We want lateral surface area as a function, or not as a function of y, let's say in terms of y. Not exactly a function, it's just an integral in terms of y. Okay, so to do that I'm going to start with my arc length. Now in terms of y, the arc length is the square root of 1 plus x prime of y sub I squared times delta y. Now this time, this is my curve, it's given by this function, but notice I need x as a function of y so I can take its derivative. So I need to solve this equation for x. Well, if I subtract 2 from both sides, I get this. And if I square both sides, I've got x equals y minus 2 quantity squared. So that's my x as a function of y. X prime requires the chain rule. Because notice I've got a function nested inside another function. This is my inside function. My outside function is that squaring function. So the derivative of a function squared is that power, you bring it down, times that function to the one less power. 2 minus 1 is 1. Put your inside function back in, and then you multiply by the derivative of the inside. Excuse me. The derivative of y minus 2 is just 1 with respect to y. So that's our x prime. So arc length is the square root of 1 plus x prime of y sub I squared times delta y. So it looks like we've got 2 times y sub I minus 2 squared. Now if I square that, I have to square the 2 and square that, because remember, if I've got a times b quantity squared, I factor each, or excuse me, I square each term, each factor, not term, I'm sorry. I square each factor separately. So I'm going to square the 2, I'm going to square the y sub I minus 2. Now I could do that. I could call that 4 times y minus 2 squared. But now I've got to write that twice in FOIL and then distribute. That's okay. We could have distributed first and then squared it. I think that would have been the more efficient way to go. But since I already talked about that, we'll just do it this way. This is just fine. I've got my 1 there, I've got my 4 there, I'm not doing anything with them, I'm just foiling here. First times first is y sub I squared. Outer times outer is minus 2y sub I. Inner times inner is the same, so I'm going to have minus 4y sub I. And last times last is a positive 4. If we distribute this 4, we get this. And then you add the 1 to the 16. Oh my goodness. This is not looking so hot. It would have to be a very special radius for us to multiply this by 2 pi times the radius and get something that's nice and easy to integrate. So I think the other method's probably better, but let's keep going. So that is our arc length in terms of y. Now remember, our surface area came from taking that strip of paper around the outside, splitting it down the side, and then stretching it out like this. So this was the circumference of that circle all the way around. It's 2 pi times the radius times the arc length. That's our surface area, that dimension times that dimension. We just found the arc length. Now I need the radius in terms of y. Ooh, actually, maybe I didn't need to do all that algebra. I think it might work out after all. Let's see. Radius is vertical, so it's the top y value minus the bottom y value, but I want them in terms of y. Remember that vertical distance from when we talked about the area between two curves? Remember how we talked about if we're at a point xy, the distance from the x-axis to that point is y. If that was the point 2, 4, just for example, well, then y would be 4, right? Because that's how tall it is, right? It's how far off the x-axis it is. So in general, this top y value is just y. The bottom y value is 2. So in terms of y, we just get y minus 2. And actually, before I did all this algebraic rigmarole, yeah, it's going to be integrable, but I don't think I'm going to need to do all of this. So keep that in mind. Let's put the pieces together now. So my surface area is the circumference times the arc length. So that's 2 pi times the radius times the arc length. And that, in this case, that's 2 pi times this, which is right here, y sub I minus 2, and the arc length would be helpful if there was a y minus 2 squared inside. And look, if this simplified version has a y minus 2 squared inside. I'm sorry, we didn't have to do all that work. It actually made it worse. It's good practice with algebra though. That's okay. So we're going to use this for our arc length. Oh, don't forget your delta y. That's part of the arc length as well. All right. So our total surface area is approximately the sum of all of those surface area pieces, the surface area of each piece. And that is the sum, as I goes from 1 to n, of 2 pi times y sub I minus 2 times the square root of 1 plus 4 times y sub I minus 2 quantity squared times delta y. So the surface area is the limit as the number of strips of paper around our solid of revolution go to infinity of this Riemann sum. Or you can think of it as delta y going to 0. Same thing. And that's the definition of this integral. We get 2 pi. That becomes a y minus 2 in the limit. This becomes a y minus 2 squared in the limit. Delta y becomes infinitely small. It's an infinitesimal change in y now. That's dy. Now, I also need bounds. If I'm actually going to get surface area out of this, well, this is going to give me a function. I need numbers here in order to get an area out. So let's look at our picture. Now these y values are not obvious. When x equals 1, clearly y is the square root of 1 plus 2, so y is 3 there. But when x equals 3/4, I don't know what that value is off the top of my head. And when x equals 15 over 4, I don't know what that y value is, but we can find it. It's not a problem. So we're going to find the y value here, and we're going to find the y value here. Oh, and actually, I think we need y to start at 0 because our region starts at y equals 0. So our bottom limit is 0. And then we're going to go all the way to the top of our region. And that's the y value that goes with x equals 15 over 4 on this curve. So to find the y value, that upper limit of integration, we're going to replace x with 15 over 4. So I've got y equals the square root of 15 over 4 plus 2. It's kind of ugly. Square root of 15 doesn't simplify. Square root of 4 is 2. So that's my upper limit of integration. It's kind of bad. Where did it go? Ah, there it is. That's okay. It's just a number. We can plug it in. No problem. Okay. So now I want to evaluate this integral, and hopefully when I do, I get exactly the same answer that I got with the other method. You can see that the integration looks a little worse, but it's actually just a u sub. So it's no big deal. Now when we are looking at this and thinking about evaluating this integral, I see a square root. So I'm hoping that this is a u substitution. I've got a function nested inside another function. The inside function here is usually my u. Now you could let u equal y minus 2, but then you'd have to substitute again. So we're just going to substitute once. We don't want to have to do a double u substitution. We just want to use a single u substitution. So I'm going to let my inside function here be u, and then I'll take its derivative, and hopefully its derivative is out here somewhere. So let's see. Let's see if it's out there. Actually, I'm going to use this other piece of paper. It's already been used. All right. I want you to see the integral that we are working on. Okay. So u is 1 plus 4 times the quantity y minus 2 squared. if I take the derivative of this, I have to use the chain rule. Derivative of 1 is 0. The derivative of 4 times something squared requires the chain rule. I've got an inside function. Derivative of 1 is 0. The derivative of 4 times a function squared is that 4 times the 2, so 8, times the inside function to the 1 less power. 2 minus 1 is 1. Substitute your inside function back in and multiply by the derivative of the inside, which is just 1, and then don't forget your dy. du is the derivative of this function times dy. So we've got 8 times the quantity y minus 2 dy equals du. Now I look at this and I compare to what's up here. Do I have this? No, but I've got a 2 and a y minus 2 and a dy. If I want to make that a 2, I'll just divide both sides by 4. So 1/4 of du turns out to be the 2 times the quantity y minus 2 dy that we have up there. All right, so I'm going to rewrite my integral. Oops, I'm not going to put that 2 there. I'm going to leave my pi here. The 2 times y minus 2 dy, I'm going to factor those off to the far right. So the pi is there, that is taken care of, that is taken care of. The only thing that's left is the square root of all of this. Okay, I want to write all of this in terms of u. Well, that is u, so that's the square root of u right there. According to this is the same as 1/4 du. So I've got pi, which I can factor outside of my integral, and I've got a square root of u, and this is 1/4 du. You're multiplying by it. So you can bring the 1/4 out front and bring the du to the far right. Now this is not quite equal to that. I want it to be equal, but it's not equal. I need new bounds. So I have to figure out what u will be when, that should be a dy, not a du, sorry guys. I have to figure out what u will be when y equals 0 and when y equals this number. So we're going to substitute. I'm going to do 0 first because it's easier. This is our new lower bound. So u is 1 plus 4 times the quantity y minus 2 squared. And we're substituting in 0. So I get 1 plus 4, negative 2 squared is 4. So I get 17. Oh, square root of 7, or I'm going to have a 17 there for my new lower bound. Okay, that's all right. Our new upper bound comes from replacing y with this ugly thing. Yeah, I think this one was definitely easier in terms of x rather than y. All right. Now let's simplify. The 2 minus 2 reduces. Over here I've got square root of 15 squared. That's going to be 15. 2 squared, because I'm going to square the numerator, square the denominator because of our properties of fractions raised to powers. 2 squared is 4, and those reduce. 1 plus 15 is 16. That's a convenient number. Is that really right? I'm a little worried that 16 and 17 makes me think I'm going to get the wrong answer. Happened. Oh well, let's see. Let's see what happens. Okay. So we're going to integrate this. The way I do that is I write that as u to the 1/2 power, and then we anti-differentiate. So we add 1 to the exponent, and divide by the new exponent. So I've got 1 plus 1/2 is 3/2. And then I'm dividing by 3/2, which is multiplying by 2/3. Then plug in 17, plug in 16, and subtract. Yeah, see, there's a problem here. 2 goes into 4 twice, I get pi over 6 here. And then I've got 16 to the 3/2 minus 17 to the 3/2. And like we did on the last problem, this is the square root of 16 cubed, and this is the square root of 17 cubed. Somehow that's not right. This is 4 cubed, which is 64. And that's going to give me 17 root 17. What was the problem? What did I do wrong? Let's go back. Let's find the problem. I think I see what happened. I was not supposed to integrate from 0 to this x value, or this y value, which was that ugly thing, 2 plus square root of 15 over 2. I was supposed to integrate from this y value to that y value. So let's find the y value right here when x equals 3/4. So I've got y equals square root of x plus 2. I'm going to plug in 3/4. Take the square root of the numerator and the square root of the denominator. Okay, so I've got a new lower bound. It wasn't supposed to be 0. It was supposed to start where the curve started, not where the region started. Ooh, that's very tricky. Make sure you start where the curve started when you're doing solids of revolution. Okay, so that's my new lower bound. So this should be a 2 plus the square root of 3 over 2. Let's see, where are my errors? This part is right. The new lower bound is wrong though. That should be a 2 plus root 3 over 2, which means this should be a 2 plus root 3 over 2. So I've got 2 plus root 3 over 2. It's not going to be 17 anymore. The 2's will reduce. I've got 4 plus, square the 3, you get a 3. Square the 4, or square the 2, you get a 4. Those reduce. And now our lower bound for u is 4. That's much better. So all those 17s I had were wrong. They need to be changed to 4s. So this is the square root of 4 quantity cubed, and that was wrong too. Square root of 4 is 2, and that's 8. Hey, isn't that exactly what we had last time? 64 minus 8 is 56. So we have 56 pi over 6. And 56 is 28 times 2. 6 is 2 times 3. And we get 28 pi over 3. Is that not exactly the same answer we got last time? Let's check. Got to go through a lot of old notes. This was the beginning of method number 2. This is method number 1, 28 pi over 3. Boom, 28 pi over 3. Okay, so we learned something from this example. Because I made a mistake. Mistakes are awesome learning opportunities. Okay, I said originally, let's let y go from 0 to that number, because that's where our region is. Nope, that's not how you handle lateral surface area. You've got to start from this y value where your curve starts and go to that y value where your curve ends. So we had to integrate from this y to this y. And I think that makes sense because it's as if we're taking that curve and we're rotating it around. The y values between 0 and here don't have anything to do with the surface area. When that curve gets rotated around, yeah, that's how we get the lateral surface area of this solid of revolution. So that's one example 2 ways. We can write the radius in terms of x or y. We can write the arc length in terms of x or y, and it does not matter what your original solid looked like. No matter how you slice it, this radius is the top y minus the bottom y, which is y minus 2. Or it's the top y minus the bottom y, which is the square root of x plus 2 minus 2. Either way, I can write it in terms of x or y, and I get the same answer.